In today's lesson, we are going to be working with radicals. So you have worked with radicals before. You might not know that that's what they're referred to as, but a radical is essentially the square root of something, or it has the root symbol. So we're going to be looking at how to work with that, with those, how to multiply, how to add and subtract. So we're just working with them a little bit more in depth than we have in the past. Right, just a little bit of an investigation before we start. I want you to go through and complete the following table. Right, so you're going to go through. You could work through it, kind of using some common sense. Right, so for example, the square root of 4 times the square root of 4. Well, that's the square root of 4 squared, but the square root and the square cancel each other out, so I'm left with 4. On the other side, you could use, again, common sense, the square root of 4 times 4, which is the square root of 16, which is also 4. So you could do that. You could just enter it into your calculator and see what you get as well. That might change for some of the last ones. But again, you can try to work through that to get an answer. So I'm not going to say pause the video because, again, this is more just an investigation. So we're going to use the magic of technology to fill in our table. And it should be ready just about now. So now we have our table filled out. What do we notice about the results in each row? Well, looking at each row, we should hopefully see that the results are the same. Right? In each row, regardless of how it's written, we get the same answer. So the results are the same. So we get the same results. So based on that, is there a general conclusion that we can make, or something that we can write that's equivalent to the square root of a times the square root of b? Well, as we saw above, if the roots are separate, like a times the root a times root b, that would be the same as if they were multiplied together under one square root, or under one root. And that's kind of going to be kind of the one of the main things that we use as we go through this lesson. This is going to be kind of like the underlying concept that we use. So just some definitions to look at. When dealing with radicals, we have what is called the radicand. The radicand is a number or expression underneath the radical sign. So right here, this x is our radicand. And this root symbol is our radical. Now, when we talk about an entire radical is in the form of square root n, where n is greater than 0. So, for example, the square root of 45. A mixed radical is similar to a mixed fraction in the sense of a mixed radical is in the form of a square root b, or a times square root b, where a does not equal 1 or negative 1, and b is greater than 0. So, for example, 3 root 5. That is the same, that is a mixed radical. So kind of like how a mixed fraction contains a whole number and the fraction, a mixed radical contains a whole number and a radical. So with radicals, so sometimes numbers cannot be expressed as fractions, right? And we call these numbers irrational numbers. So any number that cannot be expressed as a fraction is what we call an irrational number. And one type of irrational number is the form root n, where n is not a perfect square. Right? So for example, if I were to take the square root of 4, I would get 2. So the square root of 4 is not an irrational number, right? Because it works out nicely, it works out as a perfect square. However, if I was to do the square root of 2, punch that into my calculator, I get 1.414213562. And even though my calculator ends there, it actually continues on. Right? So this is what we call an irrational number. It's a decimal number, it's non-terminating, it means it goes on forever. So when we have these terms, which we call radicals, they're a specific type of irrational number. Now, we can find the approximate value for these irrational numbers using a calculator like I just did, right? The approximate value of root 2 is 1.414213562. I could round that to 1.4, right? Or round it to however many decimal places I need, but it's still going to be an approximate value because the decimal never terminates. The decimal never ends, right? So there is more values, we just don't see them because our calculators aren't strong enough. So if we need an exact value, right, some questions may need the exact answer. We don't want the approximation, we need the exact value. If so, we want to leave our answer in radical form. Now, that doesn't mean we're going to leave every radical without touching it, because sometimes radicals can be simplified by removing perfect square factors, right? So if I have root 4 as a factor, I can remove that because that simplifies to 2, right? So if we remove perfect square factors, we would get what we call, as we mentioned, a mixed radical, which would be a simplified form, right? So we can simplify it and still have it be an exact answer, even if it's mixed. And that's going to be our goal. So in order to do that, we need to be familiar with our perfect squares. It's not necessary, but it definitely is helpful. I'm not going to say it's not necessary. It is necessary. It's not necessary that you memorize them, but it is going to be very helpful because these are the values that or the factors that you're trying to look for when you deal with simplifying radicals. So it's very important that you do know at least what perfect squares are because you are going to be looking for them. So the first thing we want to do, or first example, we want to express each radical as a mixed radical in simplest form. And the hint that we're given, remove the perfect square factors. Right, so let's start with that. I have root 50. I want to break that up into factors where there are perfect squares. So for example, I can rewrite root 50 as root 25 times 2. 25 times 2 is 50, so I could break it up like this. Based on the initial property or that kind of generalization that we talked about at the very beginning, I can break this up into the square root of 25 times the square root of 2. It's the same thing. This, though, allows me to simplify the square root of 25, which is a perfect square, to 5. And I'm going to leave the other radical, root 2. I can't simplify that any further. So root 50 simplified is 5 root 2. I'm going to try to do the same thing for b, where we have root 27. Again, my goal is to break it up into factors that have perfect squares, or into perfect square factors. So I can break up 27 into 9 times 3. 9 being a perfect square, so I can separate it, say root 9 times root 3. Root 9 simplifies to 3. Root 3 can't be simplified any further, so I leave it. So root 27 becomes 3 root 3. For C, we're dealing with square root of 180. I want to try to simplify this. If we look at our square roots, or our perfect squares, the largest one that we can use is 36. 36 times 5 is 180. We can break this up because square root of 36 times square root of 5. Root 36 can simplify to 6, and root 5 stays root 5. Now, if you didn't recognize that 36 was the greatest perfect square factor of 180, right? Maybe you don't know, right? Maybe that's not what you're not looking for. You're looking for smaller numbers. 180 is a bigger number, so you might not know the factors of 180. You could work through it in kind of like a progression, similar if we were trying to find the greatest common factor and we didn't know what the largest value is. We can work at it in smaller increments. So for example, and it does take longer, but if you don't know what the greatest perfect square that goes into 180, yes, you could kind of work through, just do 180 divided by, say 49, divided by 64, divided by 81, divided by 36, and see if you get a nice value. But if not, you could work through it kind of in a progression. Right? I know that I can do 9 times 20. I know 9 is a perfect square. 9 times 2 is 18. 9 times 20 is 180. So I can break it up like that. I could then break up 20 into 4 times 5. Right? Because 4 times 5 is 20. 4 is also a perfect square. So I could simplify this as saying root 9 times root 4 times root 5. Root 9 is 3, root 4 is 2, root 5 is root 5. 3 times 2 I can simplify to 6, and root 5 would stay the same. So again, if you don't know the greatest perfect square, it is easy to kind of figure out if you just divide this value by the perfect squares and see what the largest one you can use, or break it down incrementally, right? Do kind of a progression, start off small, and then multiply your perfect squares at the end. So different ways you can kind of reason through it. Next, we're going to look at adding and subtracting radicals. Right, so it is going to require our knowledge of what we just kind of looked at in some cases. And it is going to be very similar to adding and subtracting polynomials. Right? When we added and subtracted polynomials, this is going back to grade 9, you could only add like terms. Right? So you had to say like 3x plus 3x would work, give you 6x, but 3x plus 3y does not equal 6xy, right? They're not like terms, right? So you couldn't do something like this. That would be a no. The other one would be yes. So you could do something like this. It's going to be the same idea with radicals. You can only add like radicals together. So for example, 2 root 3 plus 5 root 7 cannot be added because they do not have the same radical. One has root 3, one has root 7. However, 3 root 5 plus 6 root 5 do have a common radical. They both have root 5s. So they can be added together. 3 root 5 plus 6 root 5 gives us 9 root 5. One thing to note, the radical stays the same when adding and subtracting expressions with like radicals. So we didn't change the root 5, right? We changed the value in front, the coefficient, you might say, but we didn't change the radical. So let's go through some examples of adding and subtracting radicals. 9 root 7 minus 3 root 7. Well, these have the same radical. Oops. These have the same radical. So I can just add my values together, or subtract in this case. 9 minus 3 is 6. Root 7 does not change, so this becomes 6 root 7. Next, 4 root 3 minus 2 root 7. Well, these radicals aren't the same. So as they are, I cannot add them together. However, what I can do is I can simplify this radical. So the first one I'm not going to touch. I can't simplify that any further. And the second one, I'm going to leave the 2, but I can rewrite root 27 as root 9 times root 3. I can simplify that further. Again, the first one I can't change. That's not going to change. 2 times root 9 is 3. Root 3 does not change. 2 times 3 is 6, so it's going to be minus 6 root 3. Now I can combine them because they have like radicals. So 4 minus 6 is negative 2, and the root 3 does not change. So this all simplifies down to negative 2 root 3. For C, neither of these are like radicals. So let's see if I can simplify them or break them down further. In this case, I can actually break both of them down. Break down the first one into root 4 times root 2. And 18 I can break down into root 9 times root 2. Again, our goal when simplifying this should be to get radicals or like radicals in the end. So this becomes 5 times root 4, or 5 times 2. And the root 2 stays. 3 times 3, and the root 2 stays. So I get 10 root 2 plus 9 root 2. Add my like, these are like radicals. I can add the value, so 19, and the radical stays the same. So 19 root 2. D, even though there's fractions in front, I'm still going to try to simplify as much as possible. Move this over a bit, enough room. So 1 over 4 root 29 or 28 I can break down into root 4 times root 7. Root 63 will be root 9 times root 7. So I can already see a like radical appearing. Plus 2/3, and 50 we had done before. Root 25 times root 2. I go through and simplify. 1 over 4, root 4 becomes 2, root 7 stays, minus 3 over 4 times 3, root 7 plus 2 over 3, oops, not root 2 over 3 5 times 5, root 2. Simplify, so 1/4 times 2 is 2/4. Root 7 minus 3 times 3 is 9/4. Root 7 plus 2 times 5, which is 10/3 root 2. The only ones that have like terms are the first two, so I can only add the first two together. So 2/4 minus 9/4 gives us negative 7/4, or negative 7/4. I don't want to say fourths. Negative 7/4 root 7 plus 10/3, or 10 over 3 root 2. So even though I can't combine these, so I'm just going to leave them separate. Similar if I had like an x and a y term and they're being added, I leave them separate. Next, we're going to look at multiplying radicals. When we multiply radicals, there's different scenarios that we can come across, so we have to kind of be aware of what they are. Main thing though, when I'm multiplying radicals together, I multiply the coefficients together, and then I multiply the radicands together. So that means in this case, 2 root 3 times 3 root 6. I multiply the 2 and the 3 together, and I multiply the 3 and the 6 together. So let's start with that. 2 times 3 is 6. Root 3, or 3 times 6 is 18, so this is 6 root 18. Now I can actually simplify this square root, or this radical, because I can rewrite it as root 9 times root 2. Root 9 is a perfect square, so this actually simplifies to 6 times 3 root 2, which simplifies to 18 root 2. So even after you multiply, you might be able to simplify your radical after. B, same idea, multiplying the coefficients together and then multiplying the radicands. So if there's only a coefficient, I'm only going to multiply those two together. Right? So coefficients, just highlight them. Because there are two terms inside the bracket, this would be considered a distributive property. So I multiply it to both terms on the inside. So this becomes 2 times 4, so 8 root 3. The next one, 2 times 5, so plus 10. And then I have root 3 times root 3, or 3 times 3, so root 9. This would actually simplify to 10 times 3, because 9 is a perfect square. So I get 8 root 3 plus 30. And because one has a radical and one does not, they're not like terms, so I can't add them. I'm going to leave them as, or leave it as it is. Let's look at C. Same idea, distributive property has to multiply to both parts. So take it one at a time. Negative 7, I'll break it down so we can see it fully. Negative 7 root 2 times 6 root 8. And then we have negative or minus 7 root 2 times negative 11. Again, multiply your coefficients and your radicands if necessary. Negative 7 times 6 is negative 42. 2 times 8 is root 16. Negative 7 times negative 11 is positive 77. Root 2 stays there because there is no there's no root or radicand to multiply in the second one. Negative 42 and the root 16 can actually be reduced or simplified to 4 plus 77 root 2. Negative 42 times 4 is negative 168 plus 77 root 2. Similar to the last one, because they are not like terms, I cannot multiply them together. Or I can't add them together, sorry. They're not like radicals. In D, right, D is multiplying a binomial with radicals, so we can't forget to FOIL. Right? Even though there's a radical in here, we're still going to treat it the same way. So first numbers, outside numbers, inside numbers, last numbers, right? So your FOIL or rainbow, however you want to call it. So I have 2 root 3, right? There is no value or coefficient to multiply. There is no radicand to multiply, so I just combine them. I don't really multiply them together. Negative 3 or root 3 times negative root 3. This would become negative root 9, right? Multiplying the radicands together. You could recognize that root 3 times root 3 is going to cancel out the roots. So this would end up being a negative 3. But we'll kind of work through it step by step. 5 times 2 is positive 10. And then 5 times negative root 3 is negative 5 root 3. So don't forget the negative in front. Treat it like a negative 1. I can combine some like terms. Right? So I have like terms or like radicals. 2 root 3 minus 5 root 3 is negative 3 root 3. Root 9 is minus 3, or negative or minus root 9 is minus 3 plus 10. So this becomes negative 3 root 3 plus 7. Then the last example, right, I have 2 root 2 plus 3 root 3 times 2 root 2 minus 3 root 3, right? So there is a shortcut to this one. We could recognize that it is a difference of squares, so we don't have to go through and do the full FOIL method, right? We could actually just kind of simplify it, right? We could think of it as an a plus b times a minus b, right? So this actually simplifies to the square root of the first term. So 2 root 2 squared minus 3 root 3 squared. This exponent 2 applies to both parts. So 2 to the power of 2 is 4. Root 2 squared is just 2, so we cancel the root. Minus 3 squared is 9. Root 3 times squared is 3. We get 8 minus 27, which is negative 19. So that's it for this lesson. Again, the main idea is just understanding kind of some of the characteristics of radicals and how we can simplify, multiply, add, and subtract different radicals. Make sure you know your perfect squares. Make sure you know your perfect squares or are aware what perfect squares are, because they will be very useful when you're trying to simplify these.